What if the smallest building blocks of the universe didn't play by the same rules as everything else? And what if the real universe was wilder than anything in science fiction? Welcome to the strange and mysterious side of subatomic science, or as it's commonly called, particle physics. The hidden quantum world smaller than atoms, where particles like protons, neutrons, and electrons behave in ways that defy common sense. The deeper we investigate the subatomic world, the crazier things get. It's a world where particles can be in a million places at once, are mysteriously linked across galaxies, and can literally pass through solid walls. Think of atoms as the Lego bricks of the universe, but inside each brick are even smaller pieces, subatomic particles, so tiny we can't see them, yet they shape everything we know. These invisible building blocks are the foundation of reality, and in the quantum world, they don't always follow the rules we expect. First up, the electron, one of the tiniest particles in existence. You might picture it as a tiny ball, but in the quantum world, it's more like a fuzzy cloud of possibilities. Particles like electrons can be in a weird situation called superposition, where they're in many possible states at once, like being in different places at the same time or having different energies. For example, an electron might have a 50-50 chance of being in one spot or the other, and at the same time, a 50-50 chance of having one energy level or another. But the moment we actually measure the particle, it has to make up its mind and settle into one definite state. Quantum superposition is one of the core ideas of particle physics. It's also one of the strangest, because it goes against everything our everyday experience tells us. Objects in the world we can see don't act this way. But in the quantum world, the hidden world of particles smaller than atoms, the laws of physics can take an unexpected turn. In our everyday life, a light switch is either on or it's off. A coin toss lands as either heads or tails. In the quantum world, a particle can exist in a superposition, behaving as if it is in multiple states at once, similar to a light switch being both on and off, until a measurement forces it into one or the other state. Scientists are using this strange quantum trick to build quantum computers, machines that can tackle many calculations at once. With them, researchers could simulate complex molecules in the search for new drugs, or handle the complex math problems that safeguard secure communications. Quantum computers could be far faster and more powerful than the computers we use today. You think one weird particle is strange. What if I told you we could link the quantum states of two particles in a mysterious way, no matter how far apart they are? This is called quantum entanglement, and even Albert Einstein called it spooky action at a distance. Einstein used this phrase to show his unease with this idea that two particles could instantly influence each other even across vast distances, because it seemed to break the familiar laws of physics. Imagine you and your best friend each have a pair of magic dice. You're in Boston and your friend is in California. Whenever you roll your die, your friend's die instantly shows the same number, even though they're thousands of miles away. It doesn't matter how far apart you are, the dice are mysteriously linked. That's what quantum entanglement is like. Two particles are connected in such a way that when you check one, the other instantly knows and matches, no matter the distance, whether it's across the room or in another galaxy. Entanglement matters because it isn't just a strange quantum trick, it's a powerful resource. Just as electricity drives today's technology, entanglement could power the next wave of breakthroughs in computing, security, and science. Sometimes particles slip right through solid barriers they shouldn't be able to cross. That's called quantum tunneling, like ghosts walking through walls. And it's not magic. Tunneling is a natural process that occurs constantly in the quantum world. Imagine throwing a ball at a wall. It will always bounce off, 100% of the time. But if that ball was a microscopic particle, like an electron, every so often it would just appear on the other side of the wall. It sounds impossible, yet quantum tunneling is one of the most important processes in the universe. The sun shines thanks to quantum tunneling. Deep inside, protons must collide to fuse, but they naturally push each other away like magnets with the same pole. Quantum tunneling allows them to slip past this barrier, join together, and unleash the energy that becomes sunlight. Without this strange quantum shortcut, stars wouldn't shine, and life on Earth couldn't exist. Quantum tunneling is essential to modern electronics. Scientists are exploring how to harness quantum tunneling to design new kinds of transistors and diodes. Quantum tunneling also lets special microscopes see individual atoms, something regular light microscopes could never do. Without tunneling, much of the technology we depend on today would not be possible. We've already seen electrons doing some pretty crazy tricks, like being in two places at once, staying connected even when far apart, and slipping through barriers they shouldn't cross. But the quantum strangeness doesn't stop there. Unlike electrons, which are not made up of anything smaller, protons and neutrons are made up of smaller particles called quarks. Without them, protons, neutrons, and ultimately atoms could not exist. Since atoms form molecules, and molecules form life, quarks are indirectly responsible for everything from stars to human beings. They are fundamental building blocks of matter. They never exist alone. They're always locked inside larger particles, like protons and neutrons. And at the subatomic scale, they're stuck together by a strong nuclear force. Quarks are the building blocks of matter and a window into the universe's origins. By studying quarks, scientists can learn about the earliest state of the universe, right after the Big Bang. In that moment, matter existed as a quark soup, before cooling into protons, neutrons, and eventually atoms. Understanding quarks helps us peek back in time to see how the cosmos transformed from that hot soup into stars, planets, and life itself. And then there are the bosons, the universe's invisible carriers of the fundamental forces between other particles, which are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. If electrons and quarks are the Lego bricks of matter, then bosons are the glue and energy that let those bricks interact, stick together, or move. Some elementary types of bosons are photons, gluons, W and Z bosons, and the Higgs boson. Elementary bosons are fundamental building blocks not built from anything else. Photons, the carrier particles of electromagnetism, carry light, and gluons, the carrier particles of the strong nuclear force, hold quarks together. The W and Z bosons are among the most challenging particles to explain. They act as the messengers of the weak nuclear force, the force behind radioactive decay, and the reactions that fuel the sun. The Higgs boson is not a messenger of a force, but permeates the universe and gives particles their mass. The Higgs boson is extraordinary because it solves one of physics' deepest mysteries: why particles have mass. Without the Higgs boson, the universe would be unrecognizable. If particles like electrons and quarks had no mass, then no atoms could form, and there would be no stars, no people, and no life. Predicted in the 1960s, the Higgs boson was the missing piece of the standard model of particle physics, finally discovered in 2012 at CERN's Large Hadron Collider. So whether it's electrons playing hide and seek, quarks locked in teamwork, or bosons delivering secret messages, they're all part of one connected, subatomic universe, where the usual rules of common sense simply don't apply. Electrons, protons, neutrons, quarks, and bosons all obey the same quantum rules. The principles of superposition, entanglement, and tunneling apply universally across the quantum world. So think of this as a game. Quarks are the tiny Lego bricks that snap together to build protons and neutrons, which sit inside the atom's nucleus. Electrons are special Lego pieces that orbit around the nucleus but don't break down into smaller bricks. They're already as small as it gets. And bosons are the invisible messengers in glue. They don't build the Lego pieces themselves, but they carry the forces that tell the bricks how to stick together, move, or change. Out of all these wild concepts, which strike you as the strangest? Share your thoughts in the comments below. And if you enjoyed this brief trip into the world of subatomic science, subscribe right now for more stories like this. So in the end, the strange world of subatomic particles is like a giant cosmic game, with quarks and electrons as the players and bosons as the messengers and referees that keep the game in motion. Even though they are invisible to us, these tiny players shape everything we see, touch, and feel. The strange and mysterious side of subatomic science reminds us that the universe is full of secrets waiting to be discovered, and every answer only unlocks even bigger questions. Each breakthrough brings us closer to understanding the ultimate story of the universe. But it turns out that the universe is far stranger and more mysterious than we ever imagined. Until next time, remember, stay curious and keep exploring. Thanks for watching.